Hi. After having discussed the anatomic and physiologic dead spaces, let's now in this video try to understand the measurement of the dead space. Measurement of the anatomic and physiologic dead spaces. Before we actually see the measurement of these dead spaces, let's just reiterate one fact. Let's emphasize on one fact, and that is the dead space, the volume of the conducting airways is the anatomic dead space, and the physiologic dead space is anatomic dead space plus the alveolar dead space. And the second fact that needs to be emphasized is that we inspire 500 ml, let's say 500 ml tidal volume. First 350 ml reaches the alveoli and takes part in the gas exchange, and last 150 ml stays in the dead space, and then inspiration stops. And then when expiration starts, the air that comes out first 150 ml that comes out is that last part of the inspired air which never took part in the gas exchange. This dead space air is coming out, and then last 350 ml is coming from the alveoli carrying the blood gases. After having emphasized on this, let us now see the measurement of the dead space volume. Anatomic dead space is measured by Fowler's method. Now this Fowler's method is also called as single breath nitrogen analysis. So Fowler's method is based on the nitrogen analysis of a single expired breath, a single exhaled expired breath. Its nitrogen will be analyzed. That's the basis for Fowler's method. First of all, why do we take nitrogen? Physiologically inert gas. That's one reason, important reason why we select nitrogen. Now, what is the method and how it is carried out? Here is a respiratory passage made up of the dead space and then the alveoli, just a diagrammatic representation at this moment. And now we are going to measure the anatomic dead space. Basis is that we inspire atmospheric air normally, and it would contain about 79 to 80% nitrogen in this inspired air, the room air. It will go through the respiratory passage and it will reach the alveoli. In the alveolar air, some of the carbon dioxide is going to get mixed. Carbon dioxide coming from the blood will come into the alveolus, and therefore let's assume that the alveolar air contains 75% nitrogen, and we are going to measure the anatomic dead space starting from the nose and mouth up to the terminal bronchiole. We are going to measure the volume of this entire dead space, anatomic dead space. And we have assumed that alveolar air contains about 75% nitrogen. 75% volume will be that of nitrogen. Now, imagine that this subject has taken a few normal breaths, quiet inspiration, quiet expiration, and now imagine a quiet expiration. At the end of quiet expiration, imagine that is the starting point. The person has quietly exhaled out. At the end of quiet expiration, of course, the lungs are at functional residual capacity. And now the next breath that the person takes, the person is given 100% oxygen. So, after the end of quiet expiration, the next breath that the person takes, would be 100% oxygen. That is, nitrogen free air will be given to the subject. 100% oxygen means nitrogen free air is given. Person inspires this air, 100% oxygen is inspired. It will reach the alveoli, and at the end of, let's say, 3 seconds of inspiration abruptly stops, and now the expiration starts. As the expiration starts, we will start analyzing the nitrogen in the exhaled air. Imagine this. This person had inspired 100% oxygen, and therefore, as we have said, that last part of the inspired air stays in the anatomic dead space, and that will be the first part of the exhaled air. So first air that starts coming out will be virtually nitrogen free, because we have given 100% oxygen, and that 100% oxygen, 500 ml or whatever volume of air that he has inspired, 100% oxygen, last part stayed in the respiratory passage, last part of the inspired air stayed here, and then the exhalation starts. That means that becomes the first part of the exhaled air. Coming from the dead space, it will be nitrogen free. And then after a certain volume has been exhaled, then the nitrogen will start coming out into this exhaled air. We are analyzing this nitrogen which is being exhaled out, or rather we are analyzing the exhaled air for its nitrogen content. So initially no nitrogen, because that was the dead space air coming from the anatomic dead space. It contains purely oxygen because we had given 100% oxygen, and then later part starts coming from the alveolus. Later part of exhalation is coming from the alveolus. That will have nitrogen in it. We will analyze it. How much of the volume did not contain nitrogen at all? It was nitrogen free. And then how much came from the alveolus? And then from that we can derive the volume of the anatomic dead space. Now let me just mention it here, that we have actually hypothesized, or we have actually assumed that there would be no mixing of air between the anatomic dead space and the alveoli. I mean, we have made a tight compartment. That's not actually the case, but we have for a moment assuming that this is a tight compartment, that this is the anatomic dead space, and then there are alveoli where gas exchange occurs. So we have made a tight compartment, and therefore we are saying hypothetically that initially, let's say, some volume that comes out will be nitrogen free, and we will take that volume as the volume of the anatomic dead space, and then the later part comes from the alveolar air, which is actually containing nitrogen. But actually it's not so, because there will be the mixing of alveolar air with the anatomic dead space air. So now let me just draw it graphically to understand this, that the last part that I am explaining, how we have assumed a tight compartment for the anatomic dead space and the alveoli, two separate compartments we have thought or taken them to be, which is not the case. Actually, what is going to happen if we look at it graphically? Plot a graph for volume of the nitrogen in the expired air, and this is the volume of the expired air. So volume of the expired air, we will plot it against the percentage of nitrogen in it, or the volume of the nitrogen. How the graph looks? It will be S-shaped. It will not be a perfectly linear graph. That is, initially 150 ml came completely nitrogen free, and then later part was completely having that 75% nitrogen. No, it's not going to happen like that. The graph is S-shaped, means initially volume of nitrogen zero nitrogen is in that air, it is coming from the dead space, and then slowly the nitrogen volume will increase as alveolar air starts coming out, and then it will reach a plateau. Now there will be a steady concentration of nitrogen in that expired air. So actually it's not a very strict compartment. Nitrogen will rise slowly in the expired air because alveolar air got mixed in our anatomical dead space air, and therefore it was a mixed air that is coming out. So what we do is we will draw a straight line passing through the median of this S shape, and it will give us the volume of the anatomic dead space. This will be the volume of the anatomic dead space, and remaining air that is coming out is coming from the alveoli. So that's how we measure the anatomic dead space by Fowler's method, single breath nitrogen analysis. Remember, the basis was this, that we gave 100% oxygen with the inspired air. It went through the anatomic dead space, and when the inspiration ended, anatomic dead space contained only oxygen because we have given only 100% oxygen. And then as the air starts coming out, exhalation starts, initial volume of air that is coming out was the last part of inspired air, and that contains only this 100% oxygen, that means nitrogen free. And then later parts that are coming out from the alveoli, and we know already that alveoli contain about 75% nitrogen, so that is already known to us, and that air will have nitrogen. So nitrogen concentration in the expired air will rise gradually, reach plateau, and then that will be the maximum concentration of nitrogen. But that first volume that came out, from that volume, which is a nitrogen free volume, we will get to know the volume of the anatomic dead space. So that was Fowler's method, or that was the basis for Fowler's method. Now coming to the physiologic dead space. Physiologic dead space is measured by Bohr's method, and we will just see the principle behind it. Physiologic dead space, or rather I would say alveolar dead space. I will explain how we measure the alveolar dead space by the Bohr's method. We took nitrogen because it was physiologically inert. Same could have been taken here. But instead, in the Bohr's method, it is expired CO2. Rather expired PCO2 in the expired air, or concentration of carbon dioxide in the expired air. A better term would be concentration of carbon dioxide in the expired air, or expired PCO2, partial pressure of carbon dioxide in the expired air. Now, why do we select carbon dioxide? Its properties for the expired air are similar to the nitrogen, that's A. So we could have chosen nitrogen, we are instead selecting carbon dioxide. A second point is room air. I mean, this is important one. Room air does not contain any carbon dioxide. That's the another important feature. Now, what is the basis for this method? We are talking about the physiologic dead space, and that would include the anatomic dead space, fine, we have already measured it, and alveolar dead space. So now we will focus on the alveolar dead space measurement. To learn the principle, we will focus on the measurement of the alveolar dead space, and let's try to understand the basis behind it. Now consider these two alveoli. These alveoli are taking part in the gas exchange. So let's say these are the alveoli which are fully functional, and they are exhaling the air, or they are sending the air out, and this is the expired air. Expired air will be collected in a bag for measurement of carbon dioxide, and from that we will analyze the alveolar dead space, which will be a part of physiologic dead space. So expired air will be collected in the bag. Analysis of carbon dioxide will be done. I have just written 10 here is 10 arbitrary units. Consider this. Carbon dioxide is coming from via the venous blood. It came into the lungs. It has come near the alveoli. Now this comes in the alveolus. Let's say both these alveoli are functional as of now. Carbon dioxide will immediately reach equilibrium from the capillary blood to the alveolus, so that the PCO2 in the alveolus, let's call it PaCO2 or alveolar PCO2, and PCO2 in the pulmonary capillary blood will be the same, because it reaches equilibrium. And then this blood will now go to the left side of the heart. Imagine this is the oxygenated blood now. So this is going to the left side of the heart, and left side will pump it into the artery. So here we are looking at the arterial PCO2. And we are saying that alveolar alveolar PCO2 is same as arterial PCO2. Imagine this, that the CO2 came into the pulmonary capillary blood and it came into the alveoli. From there it's going to be exhaled out. It reaches rapid equilibrium between the pulmonary capillary blood and the alveolus, and then it goes to the left side of the heart. Then it goes to the arterial blood. So arterial PCO2 and the alveolar PCO2 will be the same. Alveolar PCO2 equal to arterial PCO2. Now we are interested in another PCO2, that is expired PCO2, PeCO2. Imagine both these alveoli are functioning normally. So this 10 units carbon dioxide came here. It's going to be diluted by the dead space air, anatomic dead space air. Let's avoid confusion. It will mix with the anatomic dead space air, and it will start coming out. So alveolar PCO2 is going to be diluted by the anatomic dead space air, and it starts coming out, and we measure the expired PCO2. PeCO2 is partial pressure of carbon dioxide in the expired air, or we just measure the content of carbon dioxide. Now consider this, both these alveoli were functioning normally. How much carbon dioxide will come from the blood, and then it will get mixed with this respiratory passage air, which did not contain, by the way, it did not contain any carbon dioxide. It is the last part of the inspired air. Inspired air was the room air, and room air does not contain any carbon dioxide. So when the air started coming out, exhaled air, it did not contain any carbon dioxide. But carbon dioxide from the alveolus then mixes with this dead space air and starts coming out. If both these alveoli were functioning, mean both these alveoli had the blood flow, and the carbon dioxide has come out from both these alveoli and is coming out. Imagine that will be 1 PeCO2, 1 carbon dioxide concentration in this expired air. And now imagine another situation whereby this alveolus is not functioning. And why this alveolus is not functioning? Because there is no blood flow to that alveolus. Second alveolus, no blood flow. So that means only this alveolus is now allowing the carbon dioxide to come through the expired air. And that means the total amount of carbon dioxide that comes out will be less, because it's going to be anyways diluted in that dead space with the dead space air. So less carbon dioxide is coming out with the mixed expired air, because one alveolus is not functioning. It does not have perfusion. So this becomes the alveolar dead space. No perfusion there, no gas exchange, no carbon dioxide coming out from that alveolus. Which means what? Which means carbon dioxide that is coming out, the expired CO2 will be less and arterial CO2 will be more, because that carbon dioxide could not come into the alveolus and it went into the arterial side, and therefore arterial PaCO2, arterial concentration of carbon dioxide will be slightly more and expired PCO2 will be or carbon dioxide concentration will be less, and therefore we are looking at, then that's the basis first of all for measurement of alveolar dead space. That's the principle, and therefore we are looking at this ratio of PeCO2 upon PaCO2, expired PCO2 upon arterial PCO2. If this is less, that means the alveolar dead space volume is more. Therefore, gas exchange could not occur in that alveolar dead space, and therefore the expired air had less carbon dioxide. And that then brings us to the Bohr's equation, physiologic dead space equation or Bohr's equation. It says the ratio of dead space volume to the tidal volume. After all, a fraction of the tidal volume is the dead space. So the dead space ventilation as the part of tidal ventilation. This ratio is equal to 1 minus PeCO2 upon PaCO2. That's the Bohr's equation or physiologic dead space equation. And it clearly tells us that if the PeCO2 is less, that means alveolar dead space will be more. I mean, that's the principle, that's the basis for Bohr's method for measurement of physiologic dead space or alveolar dead space, and method is based on expired PCO2 or expired air and its carbon dioxide concentration. So these are the methods for measurement of anatomic and physiologic dead spaces.